Hello, this is Patrick O'Shaughnessy, and this is the 10th module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. We're going to focus now on the statistical test, or otherwise known as the hypothesis test. This module will also discuss the concept of power and sample size, and discuss random sampling. As shown here in our module map, we're now at the final module of the grouping called statistical tests. As you can see here, we started with module 6 and then 7 and then 9 and now finally 10. It is highly recommended that you review 6, 7, and 9 before seeing this module to gain the most out of it. Again, statistical testing is something of an art form as well as a science. You have to know why you're doing what you're doing as much as what you're doing. And so you need to understand the background to the concepts brought up in this module as described in those previous modules here. Thank you. Okay, so what is a statistical test? Again, the whole idea behind statistics is we just don't know everything there is to know about the population. If we did, there would be no need for statistics. We would know the absolute average, for example, and we would know it would be different from the absolute average of some other population. Since we're taking samples from those populations, there's always some amount of doubt as to whether or not we are truly capturing, so to speak, a sample that is truly representative of the population. So that is what essentially associated with statistical testing. So it involves a hypothesis. First of all, in this case, an alternative hypothesis, which is typically the thing we're interested in. Is there a difference? A statement about the mean level of the population. It's different from, or it's greater than, or it's less than some number, for example, or less than or greater than some other mean. Likewise, there's the null hypothesis, which means that there is a statement about the mean level of the population equal to some number, and or perhaps it is equal to some other mean, meaning there is no difference. There's null hypothesis. Now, a test statistic is used to determine the rejection or not of the null hypothesis, as we'll see. And there is also going to be a rejection region within which this test statistic is applied in order to determine this rejection or not. And then finally, there's a conclusion about the decision made on whether to accept or reject this null hypothesis. Okay, let's try to apply this basic understanding to an example. Again, just kind of in general at this point, we'll get into the details as we go along, but let's say the EPA wants to know if a chemical company is in compliance with air pollution guidelines. So they're going to go out and take a variety of measurements around the perimeter of that chemical company. And the idea is that the measurements should not exceed 3 parts per million on average. That should be stated. So they go and take the measurements. And again, the question is the mean greater than 3 or is it equal to 3, which would be the null hypothesis. Again, we're talking about the mean here. This is identical to this concept of the sampling distribution, which is the distribution of the means. And that's what we're going to apply ultimately in a testing of this situation. So right now, all we care about is, are the means of our measurements somewhere around 3, in which case we can't say there's an exceedance, or are we definitely confident that they're greater than 3, in which case we can say, no, the population of measurements we took do not consist of a population, if you think about it this way, a population of measurements with a mean of 3. The population of measurements I took has a mean greater than 3. That is the distinction we're trying to make here. So this is also a one-directional situation. We're interested in greater than the value. We don't care about less than, or if they're just kind of different from or not equal to. We'll get into that also. So confidence intervals, on the other hand, are a two-directional test, and we can talk about those as well. Okay, so for this particular investigation by the EPA, they have to recognize that in their assessment of just a sample of the atmosphere, because there's no way to get at the entire population of it, they could have two correct decisions and two potential incorrect decisions. The two correct are that the mean of all these concentrations is greater than 3 truly, and their test results support this. Okay, correct. Or the mean is truly less than or equal to 3, and the test results also support this. Either way, it's correct. The two incorrect decisions are the mean is greater than 3 truly, but the test results don't support that. They show that they're less than 3, for example. And conversely, the mean is truly less than or equal to 3, and the test results do not support this. So we have this null and alternative hypothesis as shown here, and it is equal to mu is equal to 3 as the null, or it's greater than 3 as the alternative. And you can see here this table, which kind of gives an indication of these types of errors and correct decisions. So the true state of nature, the company is not in violation. H0 is true. Mu is equal to 3. We're okay. It's around 3 part per billion. As long as we don't exceed it, we're fine. That's what this first column is. But the EPA says, no, the company's in violation. Reject the null. That is what is known as a type 1 error, incorrectly rejecting the null. The other type of error is the company is in violation. The concentrations truly are greater than 3, but the EPA comes back and says, nope, the company's not in violation. Do not reject H0. It says incorrectly not rejecting. So that's what's known as a type 2 error. And you can see the two correct decisions are here and here. So you might ask yourself, which is the worst of the two errors? A type 1 error, a type 2 error? It can go back and forth depending on your philosophy, but from the standpoint of statistics, a type 1 error is the answer. In this case, the EPA is going to fine this company potentially for being in violation when they weren't in violation, as versus kind of letting them off the hook with the type 2 error, just again thought of as a less egregious problem than incorrectly fining them. Okay, so let's just talk about these a little more in detail. So the type 1 error, you're rejecting the null when the null is actually true. You should not reject. H0 is true, but you reject it anyway. Something is determined to be different when it's not. And we want a low probability of occurrence, and we call that probability alpha. Type 2 error, you didn't reject when H0 is false, therefore it should have been rejected. Something is determined to be not different when it is different. So we're willing to accept a slightly higher probability of occurrence of this, and we call that beta. So furthermore, when we are going about this process, again, we don't want to have a type 1 error. We don't want that to occur. So we want to have a lot of confidence when rejecting the null. We want to be highly confident that we are correctly rejecting. That's what's known as, again, this is, excuse me, that's what is desired. Okay, so we may apply, say, a probability. We're hoping for a probability of 95% of being correct. So that's a 5% chance of being wrong, right? So in this case, of 95% confidence is also saying I have a 5% chance of error. The type 1 error is equal to 5%. And just a note here, there's actually no confidence in accepting H0. As we will see with these statistical tests, all of the testing is associated with reject or not rejecting. not saying that H naught is true. We never say H naught is true. We just say we can't reject it, which seems like a bit of semantics, but we'll see it. As, for example, the jury analogy as shown here. In that case, H naught is the defendant is innocent. That's how we operate in this country. You go in, you're innocent until proven guilty, right? So HA, the alternative, the defendant is guilty. So we want high confidence in rejecting H naught. This gets back to that type 1. Which one is worst? Which one is worse? Incorrectly rejecting the null when it is true. In other words, the defendant is innocent. You found them guilty. You put them in prison, right? That's a type 1 error. The type 2 error is you let the person off when actually they are guilty. So again, that's the type 2 error, not as bad as the first one. I hope you agree. Okay, so we want to, again, high confidence in rejecting H naught. And back to this idea of confidence, again, even in the court system, they don't come back and say the defendant is innocent. No, they never say that. They say the defendant is not guilty. So again, even in a court, the onus on the jury is not to figure out whether they're innocent. It's to figure out, are they guilty, or there isn't enough evidence to suggest that they're guilty, right? Which is not guilty. Defendant is never declared innocent. It's because you have little confidence in that, and what's the point in a sense? So the same thing is true in statistics. Okay, one other term associated with errors is actually its inverse, which is the power. So in common terms, power is the ability to detect departures from the null hypothesis when they exist. Okay, so that minimizes a false rejection. Right? In statistical terms, it's actually a probability. It is a percentage. You have just like 95% confidence of properly rejecting. Here's the probability of rejecting H naught when in fact it is false. And so again, you would like that to be fairly high. So power is inversely related to beta, which is the type 2 error. So there's a simple relationship between them. If beta is 20%, then power is going to be 80%, for example. Okay, so let's get a little deeper into this. We call the formula for the standard error is standard deviation divided by the square root of n. And this has to do with, right, the standard error is associated with kind of the standard deviation of all those means if you collected a bunch of mean values as given in the previous module. So if your sample size n increases, as you can see here, the standard error is going to decrease. You have a bigger number in the denominator, you're going to divide by more. Your standard error is going to go down. If your standard error goes down, then the width of the sampling distribution gets smaller, again as shown in the previous module. So as your width of this distribution, it's easier to distinguish one of those distributions from another one. It's easier to detect differences between sampling distributions. Your power has gone up. There is a kind of the split out between them gets finer and finer, easier and easier to detect the differences as your sample size goes up. And it's interesting, that seems intuitive, and it's also built right into the equation. If the standard deviation of the sample of n observations decreases, the standard error also decreases. So likewise, if the numerator value goes down. So that's also helpful. However, the standard deviation is something tuned into the population. We can't, it's very difficult to have a scenario in which you have control over the standard deviation. So if you want higher power, greater ability to detect departures, increase the sample size as much as you can. The standard deviation, again, is typically not adjustable. It's a feature of the population. We just can't get at it that way. Okay, now just on to some typical values. As I've been mentioning, alpha is often, just historically and typically, given a value of 0.05. So you'll see that in testing quite a bit. The opposite of that is 95% confidence. that you're correctly rejecting, and then beta is typically around 20%, so there's a chance of incorrectly accepting H naught, and the power is 80%. So those are, again, fluctuate, but alpha is something you can pick. Specifically, beta and power are a little fuzzier that way. They come into play early on, actually, when you're planning your experiment, and you can do some numerical analysis of power relative to your sample size in order to make sure you have enough sample, your number of observations in your sample. But it's not really something that you can just say, I want a power of 80%. Well, yes and no. I don't want to go any further into it than that. However, there's no feature in Excel, as it says here, to compute power, and so that's a big downside to Excel. And you'd have to go on to other types of stat software packages to get at it, except for the most simplest of tests. For that, you could use, again, a general rule of thumb that, if your sample size up around 20 or more, you're probably in good shape in terms of a high power. Okay, now you're going to go out and start collecting some data. The experiment needs to be conducted in a way such that the observations collected represent the distribution, right? In this case, of the contaminant in the environment, for example. You need to have a collection of observations that should represent some of the lowest values, all the ones kind of in the middle, packed in the middle, and some of the larger ones, in order to be able to tease out a really good feeling for what the population distribution looks like. So that always has to be kept in mind, not to apply any kind of methodology that might bias you towards the high end or towards the low end, for example. Okay, so they should include low, mid, high values, encompass that of the population sampled from. They should also be independent of each other. By that I mean every time you go out and grab a sample, there is nothing about how you grab that sample now that will influence the next sample you take. They should be independent of each other. And there are time sequence situations where that may not be true, for example, and that's difficult to deal with because we live in a universe that's controlled by time, and so we can't avoid that of one sample necessarily being sampled after another sample. But that is something to be considerate of. And finally, of course, there should be some sort of way of randomizing the collection system. So that is necessary to exclude, again, the possibility of biasing the sample one way or the other. Okay, so for example, here in Iowa, we're going to use a new fertilizer for corn plants, and we want to know whether they now grow taller than 8 feet, for example. So this kind of a experiment is going to involve random sampling from a population of corn plants in a field. And we're going to assume the field is so big that there's kind of an infinite number of corn plants to be chosen for the sample that we collect. So maybe one approach, again, in order to not bias your association, is to use a blindfold. Go out and just randomly grab 20 corn plants to measure their heights. The resulting histogram of the measurement should, again, you'll never know, accurately represent the distribution of all corn heights in the field. But, again, by choosing each one this way, the resulting measurements will be independent. So the subsequent measurements will occur on either side of the mean level, meaning the next time I go to grab one, it's going to be maybe lower than the mean of all the ones I previously grabbed, or maybe it's going to be a little higher. You're going to be bouncing around, in a sense, if you can imagine it that way, around the mean. One measurement is not related in any way to the previous measurement. They are independent. Okay, here's non-random sampling. You use a direct reading instrument to measure carbon monoxide levels. And you have a sample rate set to 1 sample per minute. You go out there and start just chunking away measurements every minute, say over a couple hours. So in that case, this is not a random go out and grab a corn plant type of experiment, is it? You are kind of at the mercy of whatever is wafting by your instrument and maybe the randomness of it or not, right? And why would you expect one carbon monoxide level to suddenly bounce around the mean level relative to the other, right? Wouldn't it be more natural to assume that as carbon monoxide levels are kind of started going up, that the next one's going to be maybe a little higher than the previous one, and then maybe they start kind of migrating downward a little bit. So they actually kind of track each other. They are not independent. So again, you may end up with a fairly decent histogram of the amounts, but they will not be independent. The CO levels will most likely not vary widely between one sample to the next sample. So the current sample will be related to or actually correlated with the previous sample. So this is something to keep in mind when you're doing, when you have data gathering of this type.